Hi, sir.
Hi, Amy. How are you doing?
Yeah, okay.
Good.
How are you?
Very good. Very good. Thank you. So, how was school?
Yeah, it was good, just a little bit, kind of getting a bit more stressful, but yeah, still
Yes.
okay.
A lot of workload now, right?
Yeah, it's only been in the second week.
Yeah, but it's a big change from such a big holiday kind of thing. You're back to school
Yeah,
and all of a
that's
sudden
true.
everything. Yeah, it makes a lot of difference.
Mm-hmm.
Yeah. Okay. So, we are discussing questions on quadratic equations. And uh, today I have some very difficult questions for you. Let's see how well
All right.
prepared you are on this particular chapter. So, are you ready for that?
Yeah, I am. Let's go.
Okay, so let's go for it. Mhm. There, you see 5 questions on the screen?
Yep.
Perfect. Can you read these questions and tell me as you go along, how are you going to solve these questions? And then we'll discuss their solution in details, okay?
All right. So question 1. Factor x to the power of 4 plus x squared plus 1.
Mhm.
Um,
How will
can
you
you
do this?
make Can you say like let y equal x squared and then work from there or no?
Well, we could do that, no problem. That step is not wrong. So then how will you factor? Do we apply product and sum in this particular case?
No.
Because 1 times
Completing
1
the
is 1
square?
and its sum is 2. So you do not get the coefficient for x. So is it factorable?
Mm. No. Oh, so if it's unfactorable, that's
Yeah.
when you use completing the square, is
Yes,
it?
you're right. So we'll
Oh,
use
okay.
the strategy of completing the squares in this particular case. That is perfect. Now, question number 2 for you.
Line y equals x plus 5 intersects the parabola y equals x minus 2 whole squared plus 1 at A and B. Find the area of the triangle ABC, where C is the vertex of the parabola. Round to tenths.
Yeah. So what is going to be your approach for this particular question?
So obviously point C would just be 2, 1. And then I would find obviously A and B by expanding the x minus 2 whole squared plus 1, make that equal to x plus 5, solve the normal quadratic, find A and B, join all the points, make a triangle, then use Heron's formula, which I need to
Perfect.
still learn.
Correct. So use Heron's formula since the triangle may not be a right angle triangle, correct?
Even if it's like obvious, isn't it always safe to use Heron's formula just to
No,
verify?
if it is a right angle triangle,
Or
just multiply 2 sides and divide by 2, right? That is much simpler. Heron's formula application is kind of tricky and it involves a lot of
oh,
calculations.
okay.
Yes.
So just to double check, how
Yes.
do we make sure that the triangle is right angle
Okay. So
if it's
let's say the
perpendicular?
points are, in this case, we are saying A and B. Let's say the points are A, B, and C. Then you have to
Yeah.
take slope of AC times slope of CB. If that is equal to -1, in that case, it is right angle. Because then they are
Oh,
perpendicular.
okay, yeah.
You could do
Let
that,
me
right?
just quickly take a picture of that.
Sure.
Okay.
So other way, of course, is to find the side lengths and square them and all, but this is fastest, okay?
That's long, yeah.
Yeah, this is fastest. Now, question number 3 for you.
Question 3. Solve 2 to the power of 2x minus 3 to the power of 2x to the power x plus 3, add 128 equals to 0.
Yes.
Yeah, so this is quite funny because today in class we did a similar like questions to this.
Good.
So what we did was it's kind of like that let y equal to something. So in
Okay.
this case, we can see 2 to the, we know, so we can see 2 to the power of 2x can be written as 2x whole squared.
Yes.
And then minus 3 would say there, and then 2 to the power of x plus 3 is the same as 2 to the power of x times 2 cubed.
That is perfect. So if you know
And
that,
then,
that is clear.
yeah. And then 128 is the same as 2 to the power of 7.
Correct.
So
And then you can, yeah,
just work from there.
good job. So the whole idea of
All
making
right.
you go through this is like, assume that this is your examination test paper, right?
Oh,
And when you
okay.
read
Yeah.
the questions, as soon as you read the questions, in your mind, a thought process starts. And in that, while you're reading, you have a strategy to solve the example, whatever the question is,
Mm-hmm.
right? And then you move forward. But the thing is, it is best to read the test paper first, go through all the questions, and then begin answering them, right? So that is what we are trying to do. I'm just fine-tuning you for the examination. Now you're perfectly
All
ready for it.
right.
So question number 4 for you.
All right. So for how many positive integers of n will n to the power of 4 minus 3n squared plus 9 be a prime number?
Yes, how will you solve this one?
So it kind of looks similar to question 1. So would we use completing the square?
Okay, you can complete the squares and then what? How will you get
Okay.
all the
So,
numbers which will give you prime numbers? That is kind of critical thinking here.
yeah, do you add 1 to
No.
the
So we'll look into this
number?
particular thing.
No.
This is a very interesting question. So we'll get
All
into
right.
details. Now, question number 5 for you.
If x plus x squared plus x cubed minus 1 is 0, then find the value of x cubed plus 1 over x.
How will you do this one?
Can we move the minus 1 to the right side and then
Okay.
factor out x?
Yes.
And then factor that bracket. Can you factor that bracket?
Okay,
The
we'll
bracket that
see
you
that.
make?
We'll see that also. So I think you
Okay.
have fairly good idea about how to solve them. And there is some difficulty in question number 4 and 5. And they are actually
Yeah.
very simple questions. So these are
All right.
taken from some very good competitive exams where admission to a good university may or may not happen based on such questions. These are very critical questions, right? So we look
All right.
into
Yeah.
the approach of solving them as we move along. So let's see the solution of the very first one, which is to factor x to the power of 4 plus x squared plus 1, right? Now, when you do the standard procedure of factoring, you apply product and sum. You're looking at two numbers, P and Q. You see their product, and then you also see their sum. In this case, the product is 1 and sum is 1. However, you only get 1 with 1 times 1, and that gives you 2, not 1. So it is definitely, it needs something more than the normal factoring procedure. So here we adopt the method of completing the squares, as you said, right? So a standard method of product and sum cannot factor this trinomial. We apply the combination of strategies learned in this chapter. We had done a couple of examples based on this. So one of the strategies was a perfect square. A plus b whole square is a square plus 2ab plus b square. Now you can see this is a perfect square. 1 is also a perfect square. But in the center, I just need 2x square, right? I need 2x square in the center. So that gives us a clue that we should be doing what? We should be adding and subtracting x squared, correct? In the equation, then we can make a perfect square. So that is one part. And the second is that once we get that kind of a half factored thing, then we can do difference of square and factor it completely. So that is what we're going to do after the end, right? So this is an excellent question. So we put it under the category factor unfactorable for the reason, right? So
Yeah.
to make a perfect square, we'll add x squared and subtract x squared in the given trinomial. So the trinomial here is x to the power of 4 plus x squared plus 1. So in that, we are going to add x squared and we are going to subtract x squared. Adding and subtracting the same thing doesn't really change it, right? But
Yeah.
when you rearrange, you observe that these three terms become a perfect square and they can be written as x squared plus 1 whole square. And we do have minus x squared, right? So now we can apply this strategy, the difference of squares. So we have a perfect square, x squared plus 1 whole square, minus the other square, which is x squared. So now I could write this as a plus b times a minus b. So I get one factor, which is x squared plus 1 plus x, and the other factor as x squared plus 1 minus x. And so I finally factored it. Perfect.
All right, yeah. Wait, could you just explain the step from the blue one to the green one again?
Okay, so this is here, what we have is, we have a perfect square. Let me write in capital, a square minus b square, right? Where a is equal to x squared plus 1. Do you see that? This is a square. A and b is equal to x. So difference of squares is a plus b times a minus b, right? Difference of square is product of sum and difference. So this is product, the two factors of sum of a and b, right? So we have a plus b times a minus b at this stage. And so we have factored them, correct?
Yeah, okay, that makes sense.
That makes sense? Perfect. So I've taken actually another example, as you said, where again we'll apply the same strategy of completing the squares to factors. So we'll again look into this process. Now here is another very interesting question. Previously, when we took some examples on finding the area when a parabola was intersected by a line, those were simpler in the sense that the triangle formed was a right angle triangle. So in a right angle triangle, it is very easy. You know the length of the sides, and you can easily find the area, especially the product of the legs, and half of it gives you the area. In this particular example, which I'm going to take, the triangle formed is not a right angle triangle. So that makes things slightly more difficult. Let's see how to solve such a question. Well, we do have a formula to do it, which is called Heron's formula, which is written as the triangle of ABC if you know the three coordinate points and the length of the sides, right? So basically, if we have a triangle, let's say we just make a triangle here, and if the sides are A, B, and C, let's say these are the side lengths A, B, and C, in that case, the area of the triangle is square root of S times S minus A times S minus B times S minus C, where S is called semi-perimeter. So you add all the sides, that gives you the perimeter. A plus B plus C is the perimeter of the triangle, divide by 2. So that gives you the term semi-perimeter, right? So that's easy to remember, half of the perimeter. So this is the sum of all the three sides, which gives you the perimeter, divided by 2, gives you half of it, semi-perimeter. So use this formula and then find the area. So it requires a lot of calculations. Normally a calculator will be allowed for such a question. Now let's look into the question. The line y equals to x plus 5 intersects the parabola y equals to x minus 2 whole square plus 1 at A and B. So let's say these are the 2 points A and B where the given parabola is intersected by the line with slope 1 and y-intercept at 5. Find the area of the triangle ABC where C is the vertex. So C is the vertex of the parabola. Round to tens. So you have to round your answer to tens. Perfect. So first step, as you said, of course, is to find the points of intersection, equating the two equations, that is of a parabola and the line. When you bring them together, factor, you do get 2 points, which are at x equals to 0 and x equals to 5. Substituting 0 and 5, now it is important that you should substitute in the equation of the line, not the parabola, okay? Because that is simpler to calculate. So substitute 0 and 5 in the equation of the line, which is y equals to x plus 5. You get the points A and B, which are shown in this particular diagram. A is 5, 10, and B is the y-intercept, 0, 5. Now, we know the vertex from the equation of the parabola itself. Vertex is 2, 1. So we know the third point C, which is 2, 1. Now, you can check that these two lines are not perpendicular. So in this particular case, we have a triangle which is not a right angle triangle. Right. So in that case, we have no other option than to use the Heron's formula, right? Well, I should not say no other options. There are a couple of ways to do it. I'll talk about that also. I can actually discuss at the moment. So what you could do also is, and that's not a bad approach, what you could discuss in this particular case, you could apply it very easily, that this is a trapezoid, correct? So you can find area of trapezoid. Where of course the parallel sides are easy to calculate. Those are the y values. Do you see that y values? Which in this case
Yeah.
is 5 and 10, right? So which is 5 plus 10 times the height, which is the distance between them. And the distance between them is from 0 to 5, which is 5, and divide by 2. So that is the area of the trapezoid. Once you find the area of the trapezoid, after that, you subtract the area, which is not required. You get my point? What area is not required is you make a rectangle like this. This is one rectangle, right? So minus this rectangle, this is a thin rectangle, and then we take away two triangles. Correct? Two triangles. One triangle and the other triangle. So if you do that, you do get area of the required triangle, which is shown in red. So just in case, if you forget the formula, which is Heron's formula, right? Sometimes it is given in the test paper also. In that case, you can apply this strategy. This is a neat strategy to find area of any polygon for that matter, right? Not only triangle, correct? So you can exclude whatever is not required and then get the one which is required. Now, since we know that these three coordinate points are given to us, we can first find the length of each side, right? So we calculated the length of each side, length of A, B, and C. So when you're trying to find the length of A, you have to use the point B and C. Normally in a triangle, with A as the vertex, opposite end is lowercase a, the side, right? So it is easy. If you write A, think about B and C coordinate points and use the distance formula, which is x minus x1 minus x2. Let me write down here now. Distance formula x1 minus x2 whole square plus y1 minus y2 whole square root. So we have used this particular distance formula right here to find A, B, and C, right? So once you get these distances, then since we need to round to tens place, you can actually work with 3 decimal places to begin with, and at the end, round your answer to 10th place. Perfect. The calculations are shown here. You can, of course, do and check the calculations. Perfect. Are these steps clear to you, Amy?
Yeah.
Good. So let's move on to the next question, which is exponential equations. So many times the concept learned in quadratic functions are applied elsewhere, and this is a great example. So whatever you're learning at this stage will be very helpful as you move forward. So keep that in mind. So especially while solving the exponential equations, some of the most difficult exponential equations will require your knowledge of quadratic functions. So here we have 2 to the power of 2x minus 3 times 2 to the power of x plus 3 plus 128 equals to 0. So the middle term here needs some more, explanation. So inside term, which is 2 to the power of x plus 3, can be written as what? So if I have 2 to the power of x plus 3, it really means it is 2 to the power of x times 2 to the power of 3, which is 2 to the power of x times 8, right? That is what it is. So we simplified this as 2 to the power of x times 8. Now, you can multiply 8 and 3 to get 24, and what you have here is an equation with 2 to the power of x. Now, if I substitute another variable for 2 to the power of x, then I get a quadratic equation, as you can see here, correct? Now, this quadratic equation can be solved using your concepts of product and sum, correct? You're now looking for two numbers whose product is 128 and sum is minus 24. And those two numbers are minus 8 and minus 16. Once you identify these two numbers, right, we're looking for two numbers, P and Q. whose product is 128, and the sum of these two numbers is minus 24. And clearly, these two numbers are minus 8 and minus 16. So when you add them, you get minus 24. When you multiply them, you get 128, right? So that gives you the factored form. And from the factored form, you get your solution, two solutions in this case for P, which is P equals to 8 and P equals to 16. Now, you substituted P as 2 to the power of x. So we'll get back to 2 to the power of x equals to 8 and 2 to the power of x equals to 16. Now, it is a question of solving an exponential equation. So, 8 could be written as 2 cubed and 16 can be written as 2 to the power of 4. Now, since the bases are same, we can equate the exponent. So, x is equal to 3 and x equals to 4 is our solution. So, that becomes the solution for this particular equation, right? So, we have solution x equals to 3 or x equals to 4. Is that clear to you?
Yeah. Makes sense.
Yeah. Next example here is, we have a long solution. Amy, can you please read this question?
Yep. So example 4, strategy for prime numbers. For how many positive integers of n will n to the power of 4 minus 3n squared plus 9 be a prime number? Factor and equate one of the, oh, sorry.
Yeah. Factor and equate one of the factors. Yeah.
Yeah, factor and equate one of the factors as plus or minus 1 to check if the other factors is prime.
That is the strategy. So if we could factor this particular trinomial into two terms. So prime number is what? Prime number is the number which has only two factors, 1 and the number itself. These are the two factors. So why not factor the trinomial into two factors and equate one of them as 1 or minus 1, right? Because, you know, if I equate one of them as minus 1, I could use negative may become a positive number, right? So there is a chance for that. So, so we'll equate it to plus and minus 1 and see what happens to the other factor. If the other factor is a prime number, then we have reached our solution, right? So in this case, we are also given one more condition, which is for how many positive integers of n. So definitely one thing which we have to take care of is that n is greater than 0, because it says how many positive integers of n. So if we come across a value of n which is less than 0, which is negative, we'll exclude it, right? We'll exclude it. So that's kind of important to understand. That is given in the condition. So now we'll begin with factoring this particular trinomial. What you notice here is that the center number is minus 3. Which is not 2 times AB. 2 times 9 is 18, right? Or 2 times 9 is 3 squared. So let me rewrite this. So we have n to the power of 4 minus 3n squared plus 9 could be written as 3 squared, correct? So that means I could actually factor this provided the center term is 2 times 3 times n squared, right? Then I can factor, which is 6n squared. Now, but this is minus 3. That really means to factor it, I should be adding 9n squared and also subtracting 9n squared to complete the squares. Perfect. That is the strategy for completing the squares. Is that absolutely clear?
No, sorry, I lost you.
Okay. Yes.
Could you start?
N to the power of 4 minus 3n squared plus 9 I've written as 3 square, right? That is 9. Now, if you look at it, it is not a perfect square. A squared minus 2ab, right? We are looking for a term which is 2 times ab in the center, where a is n squared and b is 3 squared. So we are looking for a term which is 2 times 3 times n square I took from here. N square. I changed the order, right? So 2 times AB. So 2 times 3 times n square means the center term should have been 6n square. Only then it becomes a perfect square. So I have to make minus 3n square as 6n square. That is what I have to make a change. How can I do that? I can do that by adding 9n squared. If I add 9n squared, I have to subtract also 9n squared. So that is how I'll complete.
9 minus, because 9 minus 3 is 6 and squared.
Yes. So that is a strategy. So what I did was that I added and subtracted 9n squared to the given trinomial, right? Well, as you were saying, Amy, we could have initially written this equation in terms of, let's say, y squared minus 3y plus 9. We could have done that also, right? No harm. But when you get,
would it work?
Yeah, when you get used to, so much of quadratic equation, you can actually move along with n to the power of 4 also. So it's not a problem. So get into the habit of working with n to the power of 4 also. It's actually beneficial.
Okay.
Right. So we have n to the power of 4 minus 3n squared plus 9 as our equation. We added 9n squared and subtracted 9n squared to complete the squares. That is the whole idea. So now if I rearrange this, that is to say that plus 9n squared I'm bringing with the term, then as we discussed just now, we see that the combination of minus 3n squared and 9n squared gives you 6n squared. And now it becomes a perfect square, and I can write that trinomial as n squared plus 3 whole square. Correct? You can expand and check. N to the power of 4, twice this will be 6n squared, and square of 3 is 9. So it really works, correct? And minus 9n squared is the left out term. Now, we again have a difference of square. 9n squared is what? 9n squared is 3n whole square, right?
Yeah.
So 9n square is 3n whole square. So it is a perfect square. So that means I can add 3n and subtract 3n to factor this particular difference of squares. So I added and subtracted 3n in my two factors. So we got n squared plus 3 plus 3n, n squared plus 3 minus 3n as the two factors of our trinomial. Is that clear?
Yeah.
Now, once we have this, then the strategy is to substitute each factor. We've got two different factors. Each factor as plus and minus 1 and see what do we get the result. Do we get a viable value of n? This is what we're checking. So, first case, I've taken the first factor, which for us is n squared plus 3n plus 3 plus 3n. I equated that to 1. Once I solve it, I do get some solution, but in this case, n is negative 1 and negative 2. Since we want n to be greater than 0, this is not treated as the solution, correct?
All right. Yeah.
Because the positive integer. The second case, let me write this. Okay, case number 2 is when I substitute this to minus 1. In that case, I get an equation which has no solution in integers, correct? So no integer solution. So we left that also. Third case, now we are working with the second factor. The second factor for us is n squared plus 3 minus 3n. So equating that to minus 1, we really do not get any integer solution, right? So we are saying no solution for that particular case. And now the last case is equating it to plus 1. When you equate it to plus 1, bringing plus 1 to the left side, minus 1 and plus 3 makes it plus 2. Now you can factor 2 and 1, right? So n minus 2 times n minus 1 is the result of factoring n squared minus 3n plus 2, right? The sum is minus 3 and product is 2. So we get a solution which is n equals to 1 and 2. Now, does these values give the other factor as a prime number or not? Then only we get a prime number, right? So substitute this into the first factor. When you substitute this into the first factor, in that case, we get 7 for substituting 1. And in the second case, when we substitute 2, we get 13. Both 7 and 13 are prime numbers, and therefore, the value of n, which is 1 and 2, works for us. Clear? And therefore, we have two solutions, n equals to 1 and n equals to 2, that results in a prime number for the polynomial. So if you substitute in this polynomial, n equals to 1 or n equals to 2, then you will get a prime number, and that will be 7 and 13. So that becomes the solution of this particular question. So that is how you have to solve it. How do you find it?
So it says how many positive integers of n?
Yeah,
Would
so
the
I
answer
have to
just
write two
be
positive
2?
integers. Yeah, so I have to write
Oh,
two positive integers. You are correct.
oh,
Specifically,
okay.
I should have mentioned this, two positive integers. That should be written as the answer. You are correct. So that
Yeah,
is what
it's
we have to
just a
do.
bit wordy.
Yeah, you are right. And that is critical because you can lose marks for that. So zero 0.5 marks are gone for that. So how many, right? So how many? So there are two positive integers of n, which are 1 and 2, which will result into a prime number for the given trinomial. Is that clear?
Yeah, it's clear.
Yeah.
It's quite different. So I
It
haven't
is
seen
very
any
different
questions
type of
like
a
that.
question. Yeah. You normally don't see such a question
Mhm.
in your books or elsewhere,
Yeah,
but sometimes in like a bonus question or in a difficult, last two questions or something like this, which you have, you might get
it
this.
will be the.
Another one which I am sharing is of a similar level, whose solution seems to be
Mhm.
very simple. But the thought process which goes into getting to this idea itself is very difficult. Now, so this is how
Oh,
you have to rearrange your polynomials and work with them. And this is a strategy which we use many times. And, Algebra 2, for example, is filled with such examples. So slightly more elevated, extreme thinking about how to work with these elements. So the question is, if x plus x squared plus x cubed minus 1 is equal to 0, find the value of x cubed plus 1 over x. So
mm-hmm.
we need to find the value of x cubed and 1 over x. How do we do that? So the strategy here is to understand that we could actually take 1 to the other side, factor, then we have every term in terms of x, right? And factor x.
Mm-hmm.
As soon as you factor, you get a value for 1 over x. See, at this stage, once you have factored, I'm taking x to the other side. So I get 1 plus x squared equals to 1 over x. Now this value of 1
Oh,
over x can be substituted here into one term. Is that clear to you?
all right. Yeah.
That is one thing. And once I do that, see, so what we do here is luckily, and the question is designed in such a way. So when I write x cubed plus 1 over x, then I'm maintaining x cubed as such. I didn't change x cubed. You see this x cubed is same as that x cubed, correct? However,
Mm-hmm.
for 1 over x, I wrote the trinomial 1 plus x squared. And rearranging, what do I
Oh,
get? Rearranging, I get x plus x squared plus x cubed, right? And we know, we have found that this step, x plus x squared plus x cubed is 1. So for these three terms, which is, I get 1. Do you see that?
oh. There's a lot of
And then,
substituting back values in.
yes, and then the 1 remains, and 1 plus 1 is 2. So it is not an easy question to solve. It's a very, very difficult question.
Yeah.
It requires a lot of skills, and especially these are specially made questions for such solutions. So once you understand this, then we can do many similar kind of questions. You get
Oh,
the idea,
okay.
right? So it is
Yeah.
a strategic
Yeah.
way. So have a good look at this and try to understand how to solve such questions, right?
Mm.
So in this series, when we are preparing you for your test, let's say this is your last test paper on quadratic equations. Next chapter for you is what? Surds, right? Indexes
Yeah.
and
So,
surds. So now we'll begin practicing questions based on index and surds. As I learned from today's lesson, it is good to share with you some tricks which may help solving difficult questions. So I'll take that next time for your next unit. But today's
all right.
lesson, did
Thank
you
you.
understand today's lesson? What is your
Yeah.
feedback on this?
It's really good. Like when you said that there will be challenging questions, you were right. So yeah, they were really different like types of questions. Obviously, I know the concepts behind what we've done, like quadratic equations and the functions and exponentials and stuff, but I haven't seen it in this kind of form. And even if it's only 5 questions, they pick up on like a variety of all the different topics, and like it makes you think a bit more deeper into the question, not just what you see face forward. So like with 1 and 4, the exponent is 4. You said you have to kind of get used to
Yes.
that. And
Correct.
whenever I see that, I always try and do the subbing in thing of the y equals x squared. But I
Yes.
don't really get anywhere with that because it's unfactorable. So it's best to do what you said, which is go with completing the square when it comes
Correct.
to that situation.
Correct.
Or do that a squared plus 2ab plus b squared, get it into that similar form. And even if it's to the power of 4, it still works the same.
Correct.
So yeah, and then with question 2, again, applies so many different concepts in that with x-intercepts and things. But what I learned mainly was about finding the area of the triangle. So first thing being, if it's obviously a right angle triangle, to check, all you need to do is take the 2 sides which intersect and make sure if the gradient is, when you multiply them, if it's -1, showing it's a negative reciprocal, it means it's a right angle. But if that doesn't happen, then if it's like some weird odd scaling triangle or something, you use Heron's formula. Quite simple, really. If I remember it, I think it was square root s, then s minus a, s minus b, s minus c. S being the semi-perimeter, so you just find the perimeter of all the sides and then divide it by 2.
Perfect.
3 exponential equations. So quite simple. I think the key to unlock it is knowing that 2 to the power of x plus 3 can be written as 2 individual things, and figuring that out. And then 2 to the power of 2x is 2x whole squared. So then you just let like another variable be 2 to the power of x and then solve. And then question 4 and 5 I found really tricky, but when you went through it, it made more sense. So like if it comes again, I would know like what to do.
Yes.
So I guess the main thing about this is what I found from question 4, where it says positive integers of n. You need to first write down that that's one of the restrictions. So n has to be greater than 0. Yeah, so if you write n equals -1, it's immediate 0 because you're not following or answering the question because it clearly says positive. And then when it says prime number, yeah, so that's when we were looking at, we did completing the square. Again, the same approach to question 1 and solved. And then question 5, again, like you said, it requires a lot of like just thinking. So when you look at it face forward, it actually looks really hard. But when you went through it, it was actually really like simple, really. But like it's hard to get that concept, especially during the exam and under that pressure. It's more about substituting back values that you've already found and then kind of putting it back and then work it out. So yeah.
Yeah, that is so true. So you have so easily summarized all those things. That is nice. And you remember Heron's formula. I'm impressed. It took me a lot of time
photographic memory.
Yes, apply this formula. It is like not an easy formula to apply, actually. It takes all the time to find the length of each side and then work it out.
Yeah.
And there is huge scope of error. So here I can just tell you one thing, which is when you recognize that there are 2 sides which are nearly at right angles, right? So you can treat them as legs of your right angle triangle. From the graph, you can get an idea of their length. I'm not saying exact value, but from the graph, you can get an idea of their length, and then you can multiply them, divide by 2 to get approximate value of the area of the triangle. You get my point? So you can write that value on this side, thinking, well, for this particular triangle, I'm expecting an area of 15 units square. So let's say you get some 5 and 3, and then you say 5 times 3, I mean, 3 and 10, for example, and 3 times 10 is 30, divided by 2, 15. So you have an idea that the area of the triangle is going to be 15. Now do all your calculations. And then if you are, far away from that number which you calculated, you have to check your calculation.
You know you're wrong. Yeah.
Because there could be a possibility of making error in these calculations. So no point after doing, so much of work. And this question will give you at least 5 minutes, 5 to 7 minutes to solve. So, and it will be worth 5 minutes. So it is worth taking the pain of, estimating and then checking your result. So that is a thing which you should remember, right? So,
Just
so with that,
one more
yeah,
thing.
yeah.
Yeah, sorry. But with yesterday, when we were talking about the triangles, you said to find the height. Do you think it's because you have to use the distance formula and everything? Do you think it's better to use the Heron's formula and just get it right, but you spend an extra 2 minutes, or do the whole distance thing and find the height and all of that?
In yesterday's
Which
question, the
one's
height was
better?
very simple. It was kind of just difference of y values. So there was hardly any calculation. Yeah. So we just did difference of y
Oh,
values
okay.
to get the height because one of the line was horizontal. So if you have a horizontal line in a triangle,
Oh,
then the height is very simple, correct? It is difference in x
right.
value or difference in y value. Most of the questions which you see in, I should say in the books or practice test will involve
Mm-hmm.
triangles where if it is not a right angle triangle, one of the side is parallel to the axis.
Yeah.
So that makes it even simpler. What in the
Oh, right.
examination, be open for the questions which I shared with you. So that could make a huge
Yeah.
difference between marks of the students. That's the whole idea.
All right.
So
Okay.
wherever
Yeah.
easy methods can be adopt them. Heron's formula is like a canon which should be used only when required.
Like that. Canon.
Yes,
Yeah, okay. That makes sense. So try and do all the other possibilities that I know, and if it
correct.
comes really bad and like I just can't work it out, then Heron's formula is the one to go to.
Sure,
Okay.
ultimate. Yes, no doubt about it. So with that,
Yeah,
we
all
can end
right.
our class, Amy, and keep sharing with me all the difficulties which come along the way so that you are never stuck anywhere, okay?
Yep. Thank you so much, sir. I
My
really
pleasure.
appreciate
And
it.
have a great day.
Thank you. Yeah, you too. Thank you.
Thank
Bye.
you. Bye.